Hello everybody and welcome to part 2 of my solar system walkthrough, and it's the 2nd of August. So we're back inside. You can see there is the cable that comes in from outside. It goes through the hole in the wall and we come indoors. Now I have my cables come out in a terminal box rather than just having a hole through the wall. Now if you're interested in making one of these, it's simply an AC wall socket box, a double box with a blanking plate on the front. The terminals are just 4 speaker terminals. They were bought from eBay for a few pounds, and then there are crimp-on ring terminals that attach the wires to the terminals. It's quite easy to make. So that is that. Oh, one thing to bear in mind, well, we have a pair for the wind and the solar, but for most people I would just recommend you stuck to the solar. That's cheaper and more reliable, as we don't get a lot of wind all the time here. So that's just that. Right, on the solar. Now outside I had the 3 100-watt panels wired in series, which gives me about 60 volts. So something to bear in mind is that when the sun is shining, there is 60 volts at these terminals. Now my charge controller can take a input voltage of up to 150 volts, so I could probably wire a couple more panels in series. And one thing to note is that if you went to a higher voltage, say 100 plus, then you'd have 100 volts at these terminals. And at that voltage I would probably want to have the wires joined inside a box where I couldn't get at the metal parts, as you wouldn't want to touch your fingers across 100 volts. So that's just for electrical safety. So here it's just 60 volts. But if you had a very high voltage, you probably want to have your connections inside an enclosed box. Now, like the AC fittings in your house, you'd want them sealed inside. Anyway, from there we have some cable. This is a 20 amp cable. Now my solar panels can only produce just under 6 amps, so this 20 amp cable is fine. You should use whatever gauge wire will easily cope with the current that you have from your solar panels. That is the short circuit current. So that's just over 6 amps, I think, in my case. The cables from there run up to the charge controller. This is just some ordinary pipe wrap, just to hide the wires. And then the wiring comes up here to my solar power cabinet. I have all my stuff inside a cabinet with a door. It's just a lot tidier. It's better to look at a white door than all the gubbins that's inside. So anyway, and we come up to, so from the solar panels I come up to an analog ammeter. It's not 100% necessary, as my charge controller has a remote meter that can tell me this information, so you don't need to have an ammeter up here. From the ammeter we go to a DC circuit breaker. It is an overload protector and a cut-off switch in one. This is a double pole circuit breaker. It's recommended to use double pole isolating breakers. It's a breaker and an isolating switch together, so it disconnects both the positive and the negative of the solar panels. This is a 10 amp breaker. My panels can only produce about 6 amps, so that's okay. But one thing to note is that these are proper DC circuit breakers. Do not use AC breakers on DC circuits, just they don't work properly, and it's the DC breakers are built differently inside, as it is harder to interrupt a DC circuit than an AC one. And these DC breakers are not that expensive. It cost me about 10 British pounds, so not that expensive. So we have a 10 amp breaker on the solar panels, and then we have a feed to the input of the charge controller. This is a 30 amp charge controller. It's an EVA 3215BN. It is the newer version of the Tracer charge controller. If you're going to use this system to actually live by, I would recommend that you bought the 40 amp version of this, as it's not that much dearer than the 30 amp version. This one cost me about 150 UK pounds, and I am very happy with it. The maximum input voltage of this charge controller is 150 volts, so my 60 volts is not going to be a problem. So you can have 150 volts maximum input on the input, and the load output, and I did say this is a 30 amp charge controller. It's 30 amps charging to the batteries, but only 20 amps to the output. And the 40 amp version is the same. You can only have 20 amps out of the output. So if you need more current on the output side, you need to wire directly to your batteries, which leads to the center connection is for the battery bank. So we have cable down here. This cable, probably I could make it thicker, but it's adequate. This was 30 amp wire, so, and it's fine. I could make it thicker. We go to a 32 amp breaker, and then we go to some heavy gauge cable. This is 16mm square cable. It's pretty tough, and then it's rated for 110 amps, and that goes down to the battery bank. The connection between your charge controller and your batteries, the cable should be as short as possible. So we go down this thick cable, because obviously this part of the circuit carries the heaviest current. Because how this works is that I can have up to 60 volts coming in at a maximum of 5.8 amps for my solar panels. So I'd have 5 amps coming from the solar panels, or 5.8 amps coming from the solar panels, going into the controller, and I would have, say, 13 to 15 volts coming out of the controller at up to 30 amps. So obviously, with the 30 amps coming out, I need to have thicker cable. So we go down to the battery bank, down here, and this is my battery box. You'll note that this battery box is indoors. It's in the house. So some considerations here. Since the battery box is inside the house, that is a no-no to flooded lead acid batteries. The ones with the vent caps where you add water. As when you charge lead acid batteries, a byproduct, it is hydrogen gas. That's the bubbles that you see in the liquid when you're charging them. Hydrogen gas is highly flammable, and if it builds up can be explosive, so the place for lead acid batteries is outside. I would only use flooded lead acid batteries if my battery box was outside and well ventilated. So indoors, I would recommend that you used sealed lead acid batteries. These are sealed AGM batteries. The AGM stands for Absorb Glass Mat. There is no free liquid inside the batteries, so if they got broken for any reason, they got the casing cracks for example, nothing would leak out, so no harmful acid would leak out. Also, since these are sealed batteries, they don't vent off any hydrogen gas under normal conditions. They have small valves inside that if you seriously overcharge them, they would vent off, but under normal conditions, they recombine the gases produced inside the battery. So they are 100% safe to use indoors. Also, batteries are expensive. These are 100 amp hour batteries. They cost about £125 each. So it's a good idea to keep them indoors for reasons of security. You don't want your batteries to go walkies, and then you have no power. So sealed batteries indoors, vented ones outdoors, or if you have a battery box that is properly ventilated. So for most people, I would go with the sealed AGM batteries. So this battery box is homemade. It's made out of old pieces of furniture that were recycled. So that's how that is. If we come down to the batteries, these are the batteries. Okay, I'm just going to show you the label on the batteries. If I can focus the camera. Right, these are Leoc AGM batteries. And here's some charging information. If you're using your system for standby use, that is, you charge the batteries up and you only use them in a power failure, say, then the terminal voltage should be 13.5 to 13.8 volts. So if you have your system as some kind of emergency backup. If you're using your system daily, which would then be called cycle use or cyclic use, then the batteries need a higher voltage charge. In this case, 14.4 to 15 volts. Remember, these are AGM batteries. AGM batteries need a higher voltage than some other types of battery, like gel batteries. These are AGM. AGM batteries need higher voltage, so up to 15 volts in this case. And the initial current should be less than 0.3 C amps. Well, in this case, C is 100 amp hours, so 0.3 C is about 30 amps. So the charging current should not exceed 30 amps per battery. Well, in my case, that is not a problem, as I could only produce 30 amps maximum between the 3 batteries. So that would only be 10 amps per battery, so not a problem there. Okay, so these are the batteries. The batteries, let me just focus again. The batteries are wired in parallel, as I have a 12 volt system, which means the plus of one battery is connected to the plus of the second battery and the third battery, and the same on the negative. 1, 2, 3. It's a 12 volt system, so in total it's 12 volts, 300 amp hours. Now, I'll come more into this later. So I have a cable from the positive. This thick cable here goes to a fuse, inline fuse. Fuse is very, very important. It's a safety device. This is 16mm square cable. This is the fuse. This is a 40 amp fuse. Now, for most people's systems, this is a small fuse. I'll explain more in a minute. So from the fuse, we go to another important thing, a main disconnect switch. battery disconnect switch. It's here. Battery bank isolating switch. This switch cuts off everything from the batteries. If there is any kind of emergency or technical problem, just switch off here and the batteries are disconnected. A safety thing again. And then the main cable goes down. You can't see it, comes out over there, and that goes up to the charge controller. On the negative side, the cable from the battery, and on the negative side I have a shunt. This is just a current measuring device, and that is connected to my battery monitor. Now, a battery monitor is a useful thing on your system, as it tells you how much current is going into your batteries, on how well you're charging them, but more importantly, it tells you about all the current that you are taking out of the batteries. That's important because you want to know how much is going in and coming out. I'll come to that in a moment. Also, we have a battery desulfator. It just keeps your batteries healthy by stopping them from sulfating up. Your batteries sulfate up mainly if you draw your batteries down to a low voltage, you use your stuff a lot, and then you don't charge them back up. So if you used a lot of load, you used your inverter a lot, and say it was very miserable weather, it was dark and you didn't get much solar, if your batteries stayed discharged for long periods of time, they sulfate up, and that's very bad for your batteries. It means they will get hard to charge and their capacity will be decreased, and if you do it for too long, you'll be looking at a new set of expensive batteries. So the moral of this story is know how much charge you're getting in from your solar panels and monitor your usage, and when the batteries are getting low, it's time to switch off the loads and wait for the sun to come up the next day, or get out your mains powered battery charger. See, so using these monitoring instruments is critical to keeping your system working efficiently. I do have a wind turbine outside, and if you're wondering, that is what this controller is connected to. It's not actually a wind turbine controller, it was my old solar charge controller. And this one is MPPT as well. But I told you, basically, unless you live in a very windy area, just concentrate on using solar. So that's how that is. Right, the next point is about inverters. I would only recommend you go with a pure sine wave inverter, especially if you're running any electronic device, that is anything other than a light bulb or a heating device, but I would not recommend using any sort of heating device. So anything else that is electronic, contains motors, speed controllers, anything electronic like laptop computers, televisions, I would go with a pure sine wave inverter. The pure sine wave inverter generates a replica of the power that comes out of your wall sockets. So pure sine wave only is what I recommend, and choose an inverter that meets your needs, but be realistic about what you're going to power with it. This is a 300 watt inverter, a 12 volt inverter, and if I used its maximum output of 300 watts, I would be drawing 30 amps from my batteries. So I have a 300 amp hour battery bank, but you can only use 50% of the rated capacity. That is to keep your batteries healthy in the long term. So I have only got 150 usable amp hours, and if I used my inverter at 300 watts, I would be running out of power in 5 hours. That's 5 hours and 300 watt inverter. So you need to be realistic with what you're going to power. So if you're going to run a lot of power, then you need an inverter that's big enough. And I would say also that if the main thing you're having on your system is the inverter, i.e. all your loads are 220 volts AC or 110 volts in the US. So if all your devices are AC powered, then I would recommend that you used a 24 volt system. The reason being is that your inverter uses only 1/2 of the current that it does on 12 volts, and a wire that can carry 50% less current is a lot thinner, and thinner wire is A, cheaper, and B, easier to handle. So if you're having an AC only system, 24 volts is the way to go, and you should start with a 24 volt system. No good starting with 12 volts then trying to convert, because you'd have to buy new equipment. Inverters work on a fixed voltage. Charge controllers can work on dual voltages, so 12 volt or 24 volt charge controller, but inverters work on one voltage only, and so do wind generators. That is a 12 volt wind generator. I have a 12 volt inverter. If I want to go to 24 volts, I'd have to replace them. As I said, the wind generator was several £100, and inverters, well, depending on what you buy, prices start at £100 plus for 24 volt ones. So if you're using AC only, go with a higher voltage. I have an ammeter in series with my inverter, so I can see the current being drawn, but I can also see this on my battery monitor, so this is not strictly necessary. And then I have an AC outlet that's wired to the inverter. It's just the one double outlet I have here. I will admit, well, I will say that my system, I mostly use low voltage equipment, 12 volt stuff, so that's why I have a 12 volt system. So mainly I only use the inverter to run mostly battery chargers and AC charging. Basically I use this mainly for plugging in AC adapters to charge my electronic devices. That's my main use of the inverter, and as a power tool charger. I do not run high powered appliances with this system on the AC side, and I do not live on this system. This is not the only source of power. We have grid power, and we use grid power for everyday living. So I will make that point strictly here. If you're going off grid, then I would go with 24 volt system, or if you're going to run your whole house, you're probably better going off with a 48 volt system. Again, for the same reason, the higher voltage that you use, the less current you will need to run things like your inverter. So if you're going, say, with a whole house system out in the country somewhere, then I would go with a 48 volt system. But for this system I'm going with 12 volts, and if you're at home I would probably go with a 24 volt system. You wire two 12 volt batteries in series, or if you're using 6 volt golf cart type batteries, you would wire 2 in series for 12 volts and 4 in series for 24 volts. Gold Park batteries are mostly flooded, so they should be kept outside, and the most popular battery is the Trojan T105. It's rated at 225 amp hours. It's a 6 volt battery. There are other similar batteries made in various countries of the world, but flooded batteries should go outside. So, to the rest of the system. This is the charge controller, as I said. On the output side, we have on the DC output side, I should say, I have a switch turning off the output, and then I go to a circuit breaker. Basically, it's just an automatic overload switch. It's a 5 amp breaker in this case. I did say that the charge controller can handle up to 20 amps on the output. So this is a 5 amp breaker, and it goes to my DC fuse box. It's a simple automotive fuse box, and then I wire out to my load devices. For a safety thing, anything connected to the positive line of the battery should have a fuse. Fuse is a safety thing. If you have an overload, the fuse blows rather than something overheating, producing smoke, catching fire, and etc. We don't want that. So, one thing about my cabinet, you'll be wondering if I show it to you, why there's a big hole in the bottom and a big hole in the top. Well, the idea is that when you shut the door, obviously electronic equipment, it handles power, produces heat, and the heat needs to escape. So we implement this simply with convection, i.e. any hot air will rise up through the hole in the top and it will draw cooler air in at the bottom. So it's just a passive cooling system. That's what that is. So this is the controller. Right, on this side here we have a temperature sensor. It has a remote temperature sensor. There's a lead going down, and underneath here, you probably can't see, but you can see here there's some brown insulating tape. Underneath it is the temperature probe, and on this side the controller has a remote meter. It plugs in there. There's a cable coming out, it goes around here to my workbench, and this is the remote meter for the tracer charge controller, and the meter shows you, we just press a button on it. Right, so we have input from the solar panels. Here it's showing 14.2 volts at 0.6 amps. The weather outside is wet, as you've seen. And we have a voltage of the battery bank, which is 13.2 volts, and we are putting 0.2 amps, 0.4 amps now into the battery bank, and this light symbol represents the DC output. So we've got the same 13.2 volts on the batteries, and we're drawing out 0.3 amps. This meter shows everything apart from the power inverter. The inverter is wired directly to the batteries. So that's how that works. So that is the remote meter. I also have a battery monitor. This is the BM1 compact from NASA. They are a maker of boat parts. So you can see here that the battery bank voltage is 13.2 volts and that we are putting a charge of 0.2 amps into the batteries. Now this meter shows the net charge or discharge. So if I was to run the inverter, then you'd see a large discharge, as that's what it's pulling from the batteries. Now if the sun's out, as well as I'm using the inverter, then this meter shows the net amount of charge or discharge going into the batteries. So I can know whether I'm charging my batteries at any time or running the batteries down. Also, this meter has a time button, and based on your charge or discharge, it gives you an indication of how many hours it will take to either charge your battery up to full or discharge it. So that's how that works. Since at the moment I'm using very little current, it shows the maximum number of hours that the display can show, and that's 199. So basically I am not actually running my batteries down. See, it says here I'm charging my batteries. So that's how that works. That's the NASA BM1 Compact. These are actually made to go on boats, but you can use them in RVs, caravans, and of course at home in solar power systems. Now you saw me turn on a light. That is an LED light. It's a 12-volt light. Again, I bought that from a boat part shop. It has a homemade paper shade on it, just to reduce glare. But I also have a DC battery charger. Runs on 12 volts. No need to plug it onto the grid. So it's a 12-volt battery charger. I have another light over there. I have USB chargers, and then I run other things. I have fans. There's another fan up there. I have some charging ports on my desk. The 12-volt cigarette lighter socket that runs the fan, that runs soldering irons and other things. That's a USB output. I use that for charging MP3 players and headphones, my iPod, and my solar power bank, and other devices that I have. So the system is very useful. As I said, I have an inverter, and things I run on the inverter are my cordless power tool adapters. I have some headphones, Bluetooth headphones, various pairs of headphones. They charge via USB. I got a heated jacket, there's an AC charger for that. I run a laptop computer, and what else? That is the main system, but I also operate a few other systems. I have these home-built power boxes. Basically, it's a wooden box with a sealed AGM battery inside, 12-volt battery. This one has a charge controller inside as well. On the front is a 12-volt outlet and a battery voltage charge meter. This is hooked up to a 50-watt solar panel that just sits in the window, and it's just like an emergency thing. If the power goes out, I have a source of power. I have various ones of these. These are all homemade. So here's another one that I built. You can see inside this one is basically a mini solar system. So inside you can see a battery. And there's fuses as well inside. There's a 12-volt outlet on the side. On the top it has LED light bulb. So that's good. I use this, say, for power cuts. And this one is fed by this 2-output solar charge controller. That's hooked up to the 20-watt panel over there. And that charges this bigger box and this smaller box. This is the same, it's a wooden box. This one has two 6-volt batteries wired in series inside, and a light bulb. So this is basically a cordless table lamp, you could say. This also has the bulb in it. There's a 12-volt 3-watt LED bulb. It's very light. And again, you can use it in a power cut. It's better than using candles, a lot safer. And I can use it if I want to go and look in a cupboard or in the shed or any other thing. So these up here are basically a mini solar system in itself. There's solar panels, there's charge controller, and batteries built in here. And then there's load, so it has an output. One output here as a socket, the other output is the light bulb. They're switched on this side, and there's fuses inside. So that's basically a mini solar system. So with these boxes, I run fans. I can plug a cigarette lighter to USB adapter in there. But with this, I also run my solar. Well, I run my 12-volt garden watering pump. This is a 12-volt water pump, and I hook it up to my water butt, and I can hose the garden with low voltage electricity. So that's just a few things about my solar system. I run mostly 12-volt things, so I use a 12-volt system. If you're going to use mains only, everything runs from an inverter, I would go with a higher voltage battery bank. You can also run 12-volt things if you have a 24-volt system. You just buy a voltage converter, a DC to DC voltage converter, and you wire that between the output of your charge controller and your load switch. So you put your converter box in here, and it converts your 24 volts down to 12 volts. So you can still use 12-volt things as well. So this is Solar Tiger with a solar information video. I hope you found it useful, and until next time, this is Solar Tiger saying thank you for watching. Thank you.